So what we're going to be talking about today is we're going to be talking about arc length in 3 dimensions and arc length in 2 dimensions, actually talking about it from the perspective of vectors and vector calculus. What we want to remember is arc length is like how long is a curve in space given between any 2 points along that curve. And so we're going to start out with that we have a function and we're going to define it as, and we'll do this in 2 dimensions. And this is x equals x of t and y equals y of t. So these are 2 parametrizations. So we're going to start out with this idea of we're going to parametrize a curve. And we're going to have our variable t is going to be between some points t1 and t2. And so the arc length of the curve is going to be given by, and you want to remember this from your Calculus 2 class, it's going to be s of t is going to equal the integral from t1 to t2 of the derivative of x squared plus the derivative of y squared with respect to t. Okay, so that's actually an equation that we utilized previously inside of your Calc 2 class. So let's now use this relationship in order to talk about vector valued functions and how do we find the arc length of vector valued functions on an interval of t from what we'll call a to b. Okay, so let's suppose that we do have a vector valued function r of t, and this one we're going to have it in 2 dimensions. So it's going to be defined as f of t I plus g of t j. And so our t is going to go from a to b. And so our arc length is then going to be given by, and this should look pretty similar actually, it's very similar. It's going to be the integral from a to b, that's our interval, just like before it was t1 to t2 to t1 to t2. And this will be f prime of t squared plus g prime of t squared. So basically our x component squared, our x component prime squared plus our y component prime squared. So very similar to that parametrization, right? In terms of like kind of conceptually as well. In the case of the first arc length, we parametrized, and when we parametrized, we basically found the square root of the x coordinate prime squared plus the y coordinate prime squared. Same thing that's going on here, okay? So kind of like the two should kind of line up as you're thinking about them. Now, if we have it in 3 dimensions, so we've got r of t is equal to f of ti plus g of tj plus h of tk. Okay, so now we've got this second formulation. Then we want to notice that we're just going to add on the third component, that third function, its derivative squared, okay, dt. All right, and that's it. All right, that's basically all that we're doing here whenever we've got to find the arc length. Very similar to doing it inside of Calculus 2. Now, let's next suppose that r of t is, now we're writing it in vector form. So instead of writing it in the standard unit as a standard unit vector, we're going to write it in the standard vector, the component form, f of t and g of t. And so what we want to see is that if I take this, so my s, right, is going to equal the integral of the square root of f prime of t squared plus g prime of t squared, okay? What you want to notice is that first, that f prime of t, g prime of t, we've got r prime of t, take the derivative of r, is going to then be f prime of t, g prime of t, okay? And then if I take its magnitude, so I take the magnitude of r prime of t, then that's going to end up equaling the square root then of each one of these squared. So f prime of t squared plus g prime of t squared dt. Okay? And so you can actually see that s could either be formulated utilizing the components f prime of t squared plus g prime of t squared, or we could actually just say that s is then going to equal, we'll take its integral from a to b, once again a to b, okay, and it will be then the magnitude of r prime of t dt. And that's it. Excuse me, that's not a dt, but that's just your dt. So notice, just substituting in the the magnitude of r prime of t, all right, in for the square root of f prime of t squared plus g prime of t squared, then gives me an alternative formulation for my arc length. So I can kind of do it either way. If I'm doing, if I'm working from components, I can utilize this form. If on the other hand I have a standard unit vector, I can, or excuse me, a standard vector, then I can utilize this other formulation. All right. Taking a look at it from 3 dimensions, if we actually have an r of t equal to, in this case, f of t, g of t, and h of t, then just notice now if I take r prime of t, that's going to equal f prime of t, g prime of t, and h prime of t. So we just take the derivatives of each individual one, and then its magnitude is going to then equal the square root of the individual components squared. So f prime of t squared plus g prime of t squared plus h prime of t squared. And then you just want to notice that that's actually equal to what was in the arc length before. So our s here is just going to be then equal to, again, the integral from a to b of the magnitude of the derivative of r prime of t dt. Okay? And so that actually is going to come in kind of handy for us when we do work later on. Right? Is the fact that this is also going to be a way to define our arc length. We'll do some substitution here, and that's going to help us out a lot. So let's actually take a look at a couple of examples to work with. So let's try this out. Let's find the arc length for this particular curve. So what I have is I have r of t equal to 3t minus 2i plus 4t plus 5j, and we'll have t be greater than or equal to 1 and less than or equal to 5. Standard vector valued function. What I'm going to do here is I'm going to find f prime of t, so f prime of t equals 3, and I'll find g prime of t, and that's going to equal 4. Okay, so now I'll write my integral. My integral is now going to go from 1 to 5, that's the bounds. The bounds have to do with t, and this will be then the square root of 3 squared plus 4 squared dt, which is equal to the integral of the square root, or the integral from 1 to 5 of the square root of, and this is going to be 9 plus 16, so the square root of 25 dt, which equals the integral from 1 to 5 of 5 dt. So that's then going to be 5t evaluated from 1 to 5, and so that'll end up being 25 minus 5, which equals 20. And so that then gives me my arc length. Okay? There it is. We'll take a look at a second example in just a second. So let's take a look at another example. We've got r of t is going to equal t cosine t, t sine t, 2t. And t is going to be greater than or equal to 0 and less than or equal to 2 pi. So we're going to be looking for the integral from 0 to 2 pi of the magnitude of r prime of t dt. So that'll end up equaling the integral from 0 to 2 pi, the square root of, and so the derivative of t cosine t is going to end up being cosine t plus or minus t sine t squared plus sine t plus t cosine t squared plus 2 squared dt. Simplifying, we end up getting the integral from 0 to 2 pi of, and this will be cosine squared t minus 2t cosine t sine t plus t squared sine squared t plus sine squared t plus 2 sine t 2t sine t cosine t plus t squared cosine squared t plus 4. All that in square root dt. Take now 0 to 2 pi. We'll combine some like terms. So notice I've got cosine squared t and sine squared t. So those two are going to add together to 1 using our Pythagorean identity. So 1. Then I'm going to have minus 2t cosine t sine t and plus 2t sine t cosine t. So they'll cancel. Then I've got plus t squared sine squared t plus t squared cosine squared t. So that's going to end up being plus t squared, and we'll factor out cosine squared t plus sine squared t, which will end up being 1. And then we've got plus 4. All that dt. This will then equal the integral from 0 to 2 pi, and that's going to be the square root of t squared plus 5 dt. I'm then going to go in and we're going to utilize a trig substitution here. So we've got 0 to 2 pi, and I'm going to take this and I'm going to pull out 1/5. So that's going to be, or excuse me, I'm going to pull out a 5. So that's going to be 5 times 1/5 t squared plus 1 dt. And so what we'll do is we'll let that equal the integral from 0 to 2 pi of the square root of 5 times the square root of 1/5 t squared plus 1 dt. That means that we'll let tan theta equal 1 over the square root of 5 t. Okay? And so that means if we go in, we're going to just divide through by 1 over the square root of 5. So this is root 5 tan theta will then equal t. And so consequently, if we take dt, we're going to get the square root of 5 secant squared theta d theta will equal dt. Inputting in, we're going to end up with, this is going to be the square root of 5, right, times the square root of 5. So we have this original root 5, we've got this root 5 here. So we're going to pull that out, and that'll be the integral from 0 to 2 pi. And then this is going to end up being the square root of tan squared theta plus 1 times secant squared theta d theta. So this will then equal 5 times the integral 0 to 2 pi. Tan squared theta plus 1 is actually secant squared theta. Okay, so that means that we're going to get secant squared theta inside of the square root. So this is going to become secant cubed theta d theta. Okay, and since we have secant cubed theta d theta, in order for us to integrate this, what we're going to need is we're going to need an integration by parts. So just as a review here, we're going to let u equal secant x. So then du is going to equal secant x tan x, or excuse me, secant theta, and du is going to equal secant theta tan theta d theta. And we'll let dv then equal secant squared x, or secant squared theta d theta. And so v will then equal tan theta. Putting this in, we get 5 times, and we have uv, 5 times secant theta tan theta, which equals, and so it's going to be v du, so that's tan squared theta secant theta d theta, which equals, and we'll use another substitution, is going to equal 5 times, and this is secant theta tan theta, minus, and this will be the integral, again, and all of these are going to be from 0 to 2 pi when we eventually get there. This will be secant squared theta minus 1 secant theta d theta, which will then equal, okay, 5 times secant theta tan theta minus, and this is going to end up being the integral of secant cubed theta d theta minus the integral of secant theta d theta. Now, for just a moment, I'm going to get rid of that 5. We're going to come back to it. We'll get back to it in just a second. What we want to notice is that this whole thing was supposed to equal secant cubed theta. So this is secant cubed theta. The integral of secant cubed theta d theta is going to equal then secant theta tan theta minus secant cubed theta d theta minus, and then the integral of secant theta d theta is the natural log of secant theta plus tan theta. All right, and so if we look here, and this, by the way, that's an integral, we'll add the integral of secant cubed theta d theta. So plus the integral of secant cubed theta d theta. And so we get 2 secant cubed theta d theta, the integral, is equal to then secant theta tan theta minus the natural log of secant theta plus tan theta. And so this ends up equaling, that means that this integral, that integral of secant cubed theta d theta, is actually equal to 1/2 secant theta tan theta minus the natural log of secant theta plus tan theta. Lots and lots of integration review here. And so now I can plug that back in here because that's actually what that value is there that I just circled. So now my integral equals, and it's going to be 5 times, and this is secant theta tan theta, or 1/2 secant theta tan theta minus the natural log of secant theta plus tan theta. But remember, and we're going to evaluate that from 0 to 2 pi, but that's in terms of t. So we need to resub. If you want, obviously, you can do your substitutions first. So we're going to go in and resub. Remember that tangent theta was going to be equal to 1 over the square root of 5t. Okay, we'll go check, make sure that that's the case. Yep. There it is. And so if we draw our triangle, we end up with, we'll have, this is tangent theta, so the opposite side will be t. So here's theta, t, this will be the square root of 5. This side over here is going to end up being t squared plus 5. So secant theta will end up equaling the square root of t squared plus 5 divided by the square root of 5. We'll plug that in now. We get 5 times, and this is going to be 1/2 secant theta, the square root of t squared plus 5 divided by root 5 times 1 over root 5 t minus the natural log of the square root of t squared plus 5 over the square root of 5 plus 1 over root 5t. And all of that will now be evaluated from 0 to 2 pi. And I'll let you do that one on your own, okay? Big thing here in terms of finding our arc length, okay, is that we went in and we just basically, well, not basically, we took the magnitude of the derivative of r of t, and that actually gives me my arc length. The thing about this is that what might take you a little while is just remembering some of those integration techniques that you learned from your Calc 2. All right? So that kind of gives you an example of some things that you might be seeing as you go in and you find your arc lengths. So there are some times in which what we might want to do is we might actually want to rewrite our vector valued function in terms of a different parameter. Specifically, we might actually want to write it in terms of where we start at 0 and we go all the way up through, say, our parameter s, all right, and have actually the arc length of the vector valued function be equal to s, right? Okay, rather than say starting at 3 and going to 5, we imagine that we actually want to start at 0, go out to a different parameter s, all right, and that might actually simplify our function quite dramatically, right? It might make calculation easier, it makes conceptualization easier, and so we might actually want to be able to do that. What we're going to look at right now is we're going to look at the arc length function, all right, and we'll talk about that in just a moment, and then also reparametrizing using the arc length function. And both of these could be very handy for us as we do more and more work with vector valued functions. So this is the equation that we'll use for the arc length function. So to define this, the arc length function, we're going to start and we're going to have that r of t, our vector valued function, is a smooth curve. Smooth basically just means that there's no breaks in the curve. Okay, so it's essentially continuous, or the idea of continuity for curves in 3D space. So then the arc length function is given by s of t equals, and this is the integral from a to t of the magnitude of r prime of u du. And so u here is a dummy variable. Okay, we're going to use u as a dummy variable, and then t is going to end up being the value, the variable that we use in the reparametrization. Okay, so you can kind of see, all right, so there's your u, and what we're basically going to be doing is we're going to be taking the integral of that, and I know it looks a lot like the arc length function, like the arc length. That makes sense, right? The difference is that we're actually going to be getting a function out of this, and not actually a value, which is what the arc length was, right? Where it was actually some kind of scalar value. Now, the other thing that we have is that ds dt, or the derivative of the arc length function, is going to be equal to the magnitude of r prime of t. and it'll be greater than 0. So it's going to be positive. And if we have that r prime of t is unit, okay, that is that, so like for example, the tangent, the unit tangent function, for example, then for all t greater than or equal to a, the parameter t represents the arc length. So it'll actually give us back the arc length. And that's going to be from the starting point at t equals a. So what we know is that basically the arc length here is going to end up being t minus a, okay? And we can establish what that function is, or what that value is for any value of t, okay? Let's actually see what we're going to actually use the arc length function for. All right, so we'll start out with actually seeing the application of the arc length function. So let's suppose that what we want to do is we want to find the arc length parameterization of the following curve. So the arc length parameterization, this is what we're talking about, is going to end up being the parameterization where the arc length of the vector valued function is equal to the parameter. Okay, and so I think it's going to be easiest to actually see what this looks like, and I'll give you the demonstration. So let's take, for example, that we got r of t is going to equal 4 cosine ti plus 4 sine tj. And this is for t greater than or equal to 0. Okay, so let's say that's exactly what we're looking at here. And so what we're going to do first is we're going to first find the arc length function. And so I'm going to have s of t is going to equal, and this will be the derivative, or excuse me, the integral from a to t, okay, of, and then we're going to have r prime of u du, okay? And so what that's going to look like is that's going to be the integral from a, or in our case, 0, because we're going to start at 0, 0 to t, okay? And then we're going to take the derivative with respect to u, so this is going to end up being 4 cosine, so that's going to be negative 4 sine t squared plus, and this is going to be 4 cosine t squared, and that's in square root because we're looking for the magnitude of that derivative, du. And these are actually u's, excuse me, u's, du. All right, and so that's going to end up equaling the integral from 0 to t, the square root of 16 sine squared u plus 16 cosine squared u du, which is just simply equal to, this will end up being 16 times sine squared u plus cosine squared u, so it'll end up being the square root of 16, which ends up equaling 4. All right, 4 du. We evaluate that's going to be 4 u evaluated from 0 to t. And so hence we end up getting 4t minus 0, which just equals 4t. Okay? And so that's the value, that's the arc length function. And what it is it's s of t. Okay, so it's s of t. Now what I'm going to do is I'm going to let s, so s is going to equal 4t, and that implies that t is going to equal s over 4. Okay? What I'm going to do now is I'm going to go back up to my original vector valued function, 4 cosine t plus 4 sine tj, 4 cosine ti plus 4 sine tj, and I'm going to plug in s over 4 for t. So this is going to be, so r of s now is going to equal 4 cosine s over 4 plus s over 4i, excuse me, plus 4 sine s over 4j. Okay? As I stated before, this function, this is actually the same curve. They're the same curve, it's just differently parametrized. All right? It's parametrized with s over 4 as, or excuse me, with s as its parameter. Okay? And what you'll see, let's go in and actually find the arc length of this function. Right? So what we'll do now is we're going to go in and we're going to say, like, let's say, for example, we want to go from s greater than or equal to 0, less than or equal to 4. Okay? Or how about 5? That'll be better. So now, if everything's worked out properly, then what we should find is that when we find the arc length of r of s should equal 5. So I'm going to go find the arc length. So I've got the integral from now 0 to 5 of, and then this is going to be 4 cosine s over 4. So that's going to be 4 times 1 over 4 sine of s over 4 squared. Okay, and that's actually negative, excuse me. All this is going to be in square root, plus, and then this will be 4 times 1 over 4 cosine times s over 4, okay, squared, and then d, in this case du, right? Or excuse me, ds, sorry, ds. And so consequently we get the integral from 0 to 5. This is now 4 times, or this is going to be negative 4 times 1/4, that's negative 1. And then, so this is going to be the square root of sine squared s over 4 plus cosine squared s over 4 ds, which equals the integral from 0 to 5 of, and this is 1, so this is going to end up being just ds. All right? And so what does that mean? That we're going to get s evaluated from 0 to 5, which equals just 5 minus 0, which we've reparameterized our vector valued function so that now the arc length of it is equal to the value of the parameter. Okay? Which might end up being very handy for us later on. So what we're going to do now, we're going to look to reparameterize the curve R. How do we do that? We're going to find the arc length function for the vector valued function R of t, and then we'll substitute the arc length function into the original vector valued function. Okay? That's it. So let's try one more time. Let's say, for example, now, okay, we have our example. We've got R of t equals t plus 3, 2t minus 4, 2t, and we're going to have for t greater than or equal to 3. So what we'll do, we'll find our arc length function. We're going to go from 3 to t. Okay, so we're looking for now s of t. It's going to equal, and then it'll be the square root of 1 squared plus 2 squared plus 2 squared dt, or excuse me, du, using our dummy variable du. And that'll then equal the integral from 3 to t of the square root of, and this is 4, 8, 9, the square root of 9 du, which is just equal to 3 du. This will then give me 3t, or excuse me, 3u, evaluated from 3 to t, which is equal to 3t minus 9. Okay, so that's what s is. So s is going to equal 3t minus 9. So what we'll do now is we'll actually set this up. So we're going to have s plus 9 equals 3t. We'll divide in through by 3. So t is going to equal s plus 9 divided by 3. And now I'm going to plug that back into my original equation. So r of s now is going to equal s plus 9 divided by 3 plus 3, comma 2 times s plus 9 divided by 3 minus 4, comma 2 s plus 9 divided by 3, which is then equal to, we've got, this is s over 3 plus 6. This will then be 2/3 s minus 1, and then 2/3 s plus 3. And that is your reparametrization. Okay? So that's the process. All right? Don't forget, right here, all right? I actually did. I'm going to erase it for you, but don't forget that once we find what s is equal to, we've got to rewrite, we've got to go solve for t. Okay? We've got to solve for t, right, to plug t back into our value of our function r. Okay? All right, so this actually completes the video. What we've done is we've found the arc length of a vector valued function. We then utilized the arc length function in order to reparameterize our curve so that we get a very handy curve. We get a curve that actually has its arc length equal to the value of the parameter.